This project includes a rapid cooling device and a rapid rewarming device for large quantities of human liver cells. These devices were designed in Senior Design 1 in fall 2021 and prototyped in Senior Design 2 in spring 2022 by Ashley Byerly, Julian Doe, Haley Gross, Peter Springer, Justin Stone, and Maxwell Stott. Our faculty mentor is Dr. Charles Lee, and our funding includes $500 from the Mechanical Engineering Department. These devices have the potential to provide a real clinical alternative to liver transplantation. By making bioartificial livers more readily available, hepatocyte transplantations could ultimately become a more mainstream approach to treating diseased livers. Additionally, readily available liver cells would streamline the testing and approval process of pharmaceutical drugs. If the devices are successful in obtaining their respective critical rates, they will let the human liver cells be vitrified, stored, and then rewarmed for easy access in biomedical applications.
Our cooling device consists of adjustable vertical plates used to compress a bag holding the cell solution, which will be exposed to liquid nitrogen vapors. The slots in the base allow for these vertical plates to move and minimize the thickness, optimizing heat transfer rates. The objective for instrumentation is to generate a live temperature plot on a PC. This is done using a thermocouple connected to an Arduino board, which converts the amplifier voltage output to temperature and then displays it on the plot.
The rewarming subsystem relies on a metal foil which is submerged in the solution prior to vitrification. Throughout the rewarming process, a copper induction coil is used to generate electromagnetic induction that heats the metal foil. Heat is then conductively transferred to the spheroid solution to perform the rewarming process.
To allow the user to regulate the rewarming rate in real time, a PWM program will be employed to regulate voltage output between the motor driver and the induction coil. This output is controlled by a potentiometer mounted on the exterior of the circuit housing.
Over the course of the semester, the team performed various cooling and warming experiments to validate the various design concepts. The cooling subsystem met and exceeded the critical cooling rate, and the warming subsystem was able to meet the critical warming rate. In future applications, the instrumentation could be updated to incorporate an extended ADC shield, and a second thermocouple could be incorporated. A controlled rate freezer could also be incorporated to streamline the cooling procedures.
We would like to give special thanks to Dr. Charles Lee, Dr. Stuart Smith, and Professor Joe Dalton for their support and guidance throughout this project. Our school email addresses are listed on the title block if anyone would like to learn more about our project.